The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Welcome to today's webinar, Introduction to Power Sources. This is the first ever webinar presented by Associated Power Technology, a division of Iconics USA. A quick round of introduction here. My name is Bishan Patel. I'm an applications engineer here at Iconics USA. We cover Associated Power Technology, Associated Research, and SCI companies. Today, we also have Syed Abidi joining us as an application leader. He's going to be the panelist for the webinar. And then we have Amanda Booth. She's the marketing assistant. She'll be the organizer for this webinar. A few webinar notes to make it easy for everyone. There's a question and answer utility where if you have any questions about the material being presented, please use the question and answer utility to ask questions. Syed Abidi will be answering these questions live as the webinar is going on. The webinar is also recorded and available on our website in a few days. If you have any issues with the audio or technical difficulties, please contact Amanda Booth using the chat box. You could also email her. Her email address listed here is amanda.booth@iconicsusa.com. Let's take a look at what we're going to cover today in this webinar. For today's webinar, we're going to start off with kind of covering what power is. What is power? We're going to take a look at how power, we're going to define power and take a look at what different configuration power comes to delivered to us by the utility companies. We're going to also be taking a look at some of the benefits of using power supplies, how we could have a clean output, clean and regulated output with low noise levels. We could also see how we could do a variable frequency, variable voltage. These are some of the benefits that we cover for a power source. Next, we're going to take a look at how to appropriately select a power supply. A lot of our customers that have need to do product testing or some kind of Energy Star testing, they need to make sure their products are tested in a proper frequency, proper voltages, and some of them may also require some line condition testing. And in the end, we're going to be taking a look at some of the standards that specify using a power supply beyond the normal requirements. So there may be requirements to run your products at 110% of the voltage. So nominally, this 110% voltage is not available from the wall outlet. So what is power? Everyone uses energy on a day-to-day basis. It takes energy to move your car. It takes energy to heat up your food. It takes energy for the light to come on. These are all energy usage. But if energy usage was converted to the amount of time, this is known as power. So the rate at which you use the energy is known as power. Power is used to define power by watts or VA. 1 watt is equal to a joule per second. Again, so the power is defined of how much energy you're using for a given amount of time. And watt is defined as a joule per second. To quickly calculate power requirements, you want to multiply the voltage that the product needs to run at times the current that the product will run at. So this is a quick and easy way to kind of calculate how much power is required for a given device to turn on. Power comes in different configurations. So if you have around your household the outlets, majority of the outlets are single phase outlets. The single phase outlets have line neutral connection. Third pin is for ground, which is there for safety. You may also have some outlets in the house that has what we call split phase. Now, split phase allows you to have 2 hots and a neutral wire, which allows for higher voltages to be present for products that require more than 120 volts. For some of the other applications like industrials and light machinery, 3-phase power is more efficient. So in 3-phase supply, you could have a Y configuration, or also known as a star configuration. 3-phase configurations have phase A, B, and C along with the neutral, and this configuration is called a star configuration, also known as a Y configuration. Another configuration that 3-phase comes into is the 3-phase delta. In the 3-phase delta configuration, there is no neutral, but it still has 3 phases of voltages coming out of 3 phases. Let's discuss these in detail. So when you have a single phase output or single phase requirement, usually the single phase outputs are meant to be line and neutral. Now the voltage presented by the outlet is between line and neutral. The ground is there for safety, for any current which may be fault current that may require to be routed to ground. So in a single phase configuration, you have 3 wires, a line, a neutral, and ground. Now the frequency of this single phase is set by the generators. In case for US is when the utility companies are generating this power, they're setting up the frequency at 60 hertz. Overseas, this frequency may change to 50 hertz. Some other places may have a different frequency. Majority of times you will see frequency listings of either 60 hertz or 50 hertz. Now, these are typically used for all around your household, for household appliances or light commercial usage, where single phase power is enough to power up your LED lights, microwave ovens, vacuums, and those kind of products. Now, if you were to look at what the single phase is, it's just a single sinusoidal wave of power being delivered between the phases of line and neutral. As I mentioned earlier, some of the products that you may see that have single phase input requirement could be a vacuum, your TV, and also some single phase motor. Again, we're trying to power up these devices. They require line to neutral voltages of either 120 or 240 or 230 volts, and providing this voltage differential between those two pins allows these products to power on. Let's talk about the second configuration that you may find in a household environment, which is the split phase power. Now, split phase power is also known as a 3-wire or single phase 3-wire connection. In this configuration, you have line 1 and a line 2, which are both providing voltages, and then you have a third wire for the neutral and also a ground available for safety. So when we call the single phase 3 wires, it encompasses line 1, line 2, and a neutral wire. Now the voltages between line 1 and line 2, which is known as the line voltage, will be 240 volts for a configuration that comes with 120. 120 to neutral is what we use to power up products that require 120 volts. If you go between line 1 and line 2, now this is where you get 240 volts. If you take a look at the diagram below, you could see phase A, or what we call line 1, phase B, what we call line 2, the voltage between these two is 240 volts. If you had products that need 240 volts, think about your dryer. If the dryer has heating element that needs 240 volts, you would need to connect line 1 and line 2 to get 240 volts. If the same dryer has additional electronics that need 120 volts, you need to go between the line 1 and neutral. In this case, this line 1 and neutral will provide the necessary 120 volts. So for a household setting or some light industry where 240 volts are required, and you also have a necessity of having 120 volts, split phase power may be what is required to be for your product. And the way the split phase power works is it has 2 sine waves of opposite polarity, and when the opposite polarity sine waves are traveling, they're actually adding up to provide the difference of voltage between line 1 and line 2. What are some examples of split phase power, input power? Think about a dryer, the dryer that has heating elements, also some motors. This may require additional power to be efficient at drying your clothes. An oven is a good example. If you have an oven, again, heating elements require you to have 240 volts across a heating element, but there may be some other electronics that require 120 volts. There's also split phase motor. These motors are more efficient because the voltage is much higher. They're able to perform much higher functions when you have split phase input power. Let's move on to a 3-phase power. You may see 3-phase power in industrial settings that have requirements to have big 3-phase motor to be powered on. It could be some heating elements, again, that have 3-phase heating elements. The output for 3-phase power is considered to have voltage between each phases. So phase A, phase B, phase C are 3 live voltages, and then there's a neutral line available. So this is known as the star configuration, also known as a Y configuration. Now the voltages between line and neutral is known as the phase voltage. So if I were to measure between phase A and the neutral connection, my voltage for this particular example will be 120 volts. If I went between phase A and phase B, Now, since I have two phases that are apart by 120 degrees, I have to multiply the voltage by square root of 3 to get the line voltages between the phase. So phase A to phase B, there's some type of voltage there. That voltage is line voltage. Sorry, that voltage is known as the line voltage, but this is a result of 120 volts multiplied by a square root of 3 to give you the line voltage. Now in this configuration, again, you have the capability of powering up products that require 208 volts, but you also have ability to power up products that require only 120 volts. So example given for split phase also applies here. You have 3 independent phases that deliver power. You also have voltages between phase and neutral to provide power for voltages that are nominal voltages. Now typical configuration for voltages could be 120, 208, or it could be also 277 and 480. So these are typical 3-phase power supplies available in the US. Next, we're going to take a look at 3-phase delta. Now, 3-phase delta for motors that are really efficient and they need a lot more power. Sometimes the motor configurations are configured into a 3-phase delta configuration. You also see this when utility power is being delivered to substations. The transformers are wired into a 3-phase delta configuration. The difference between a 3-phase Y and delta is that delta configuration does not have a neutral, and the wiring diagrams have phase A, phase B, phase C. I will see no neutral on the delta configuration. The only voltage available to you is between the phases, also known as the line voltage. There is no phase voltage available for these units in the delta configuration. The only voltage available is the line voltage between each phases. These sine waves are still 120 degrees apart, delivering power at the same time. Some examples of 3-phase power. I mentioned 3-phase motors. These 3-phase motors allow you to kind of efficiently deliver power or use power because there's no downtime. There's always one leg which is active, keeping up the electromagnetic field around the motor to make it keep spinning. There's also water heaters. They're wired up to 3-phase. If you had a requirement to heat up water really fast or heat up water for big industrial settings, you need to have 3-phase power to kind of quickly heat up the water for you. And then fryers are also a good example of having 3-phase input power. So far we covered power and some of the power configurations. Want to have Amanda come in and put up a poll question about what kind of typical configurations do you work with or you see around you in your settings.
Hi, Bashan. The results are in. Okay, so what are your typical power configuration requirements? 43% said single phase, 43% said single phase 3-wire. Nobody responded to 3-phase Y or 3-phase delta, and 14% said other.
Okay, thanks everyone for taking the time out to do our poll question. And it's good to know that if many of you are working with single phase, split phase, these are more common. And when it comes to 3-phase application or 3-phase products, these are much more involved products and typically, usually in an industrial setting is where you'll see these. So let's move on to the differentiating the power. Power comes in 2 fashions. There's a real power and there's an apparent power. What is real power? Real power is defined as the amount of work that's being performed when the power is being delivered. So this is measured in watts. If you were to do a calculation of how watts is measured, you have to get the DC component of voltage, the DC component of the current, and when you multiply this, you're going to get a power in form of watts. So this is the actual work that's being done. If you take a look at an example of a heating element, what does a heating element do? Heating element, it restricts the flow of the electrons, and in doing so, it heats itself up. So when you're having current flow through this heating element, the electrons kind of energize the heating element, and the heating element is releasing energy. Now, this is purely resistive load. You're going to get majority of the power that you deliver to this heating element is going to be used to heat up the environment or heat up the stovetop or oven in this case. So this is what we call real energy being used to deliver real power. On the other side, there's apparent power. Apparent power is a way of looking at power that's necessary to deliver the real power. So in a case of motor, when a motor needs to turn on, it's an inductive load or maybe a capacitive load. This capacitive load requires a particular amount of energy to power it on. So when you first power on a motor, there's a necessity for some current to turn the motor on, and this allows this apparent power to show up in your calculation. The way to measure apparent power would be to kind of measure the AC voltage and the AC current, RMS values, and the difference between how far behind the current waveform is to the voltage being applied. That's the measurement of the apparent power. Now this is a vector sum of measuring how the apparent power is being calculated. The total power required is a combination of watts that are required and the apparent power that are required in the terms of VA. So if you ever see power requirements that are listed in VA, you know that this component has some kind of resistive element, some kind of capacitive or inductive element, which will allow it to have a rating for voltage times ampere. If you have just a purely resistive load, you're going to see watts listed on it. And then an example below, you'll see that you have a 60-watt light bulb. So most of you are familiar with a 60-watt light bulb. In this case, when you have a 120-volt source applying voltage to your light bulb, it could, since this is a purely resistive element, there may be some minor component for capacitive in here, but let's just assume it's a purely resistive component or product. You're going to have a power factor of 1. The power factor is how efficient is this product in converting the energy that it receives into the energy that it dissipates. So for a 60-watt light bulb, you're looking at 0.5 amps of current draw, and the true power factor is 1, and this gives you a power of 60 watts. Now, for example, if you had a PC, in PC, there may be some power supplies in there that need to power on, or some capacitive components in there. When you're applying 120 volts to a PC, this may have an apparent power of 240 volts. Now, this is a power requirement to power up the PC, but the true work that's being done by the components inside of the PC may only be 156 watts. So again, the total power consumption for a PC may be rated at 240 watts, but the real work that's only done on this, the real energy that's being used to heat up the components or do some work, it may be only 156 watts. This gives you a power factor of 60.65. So this is not a resistive product. This is not a purely resistive product. It's more of a resistive and capacitive product. I apologize for this Windows notification. I'm going to postpone it for 4 hours. All right. So how do you measure watts? You need to measure watts using a watt meter. Some of the power supplies that are out in the market already have these meters built in. They will have a real component built into it. They will have a apparent power measurement done with VR voltage RMS and current RMS, and then they also measure the true power requirement in VA. Let's take a look at some of the examples of products you may see and how their watts are listed in their product specifications. So take a cell phone charger, for example. The power input may specify 120 volts or 230 volts, but the current draw for this product is really low, usually less than 0.1 amps, and you may see the power rating listed on your cell phone charger or iPad charger or some of these chargers, it may list anywhere from 5 watts to 10 watts. So this is the amount of energy required to power off this cell phone charger. For household vacuums, you need a lot more current. You need a lot more current for that vacuum to do its job. At this point, the current may be anywhere from 6 to 12 amps, and the power requirement in this case may be a VA listing of up to 1420 VAs. Now, these are approximately what current draw you may see for oven ranges or water heaters, but it's good to pay attention to the power requirements and know what kind of product it is. So for a water heater, again, it's a heating element. It is purely resistive product. You're going to see 450 watts listed. This tells you that required amount of voltage and the current for this. Since we talked about what power looks like in watts and VA, let's take a look at an example of what input labels you may see. Many of you don't work with three-phase power, but if you have to ever take a look at a three-phase input plate for a motor, this is the top left here. The motor may have a listing of voltage it needs, 230 volts or 460. It may have a listing, it does have a listing of 60 hertz listed, or any frequency that it could handle. And the currents are usually listed. Now, these are steady state currents that are listed. And we want to be careful when we define inductive loads or capacitive loads, because they may also have some additional inrush current that are not defined on the input plates. So we'll take a look at later on how inrush current affects ability to source out your products. To the top right, you'll see split phase, single phase 3-wire configuration. Now, just knowing that it's 240 volts, that kind of tells me this unit is going to take a line 1 hot, a line 2 hot, and the requirements for this product is 60 hertz frequency and 13.5 amps. So again, this is split phase, also known as single phase 3-wire connection. I need 240 volts. And the current requirement for this product listed out in the input label is 13.5 amps. Now, this may be the worst case scenario, so it doesn't necessarily mean this is a steady state, or this could be the maximum power that this unit could draw. The example below is for a single phase line neutral connection. Again, single phase, which is line neutral. This product is a medical device. It'll show at the bottom the voltage range for this product is from 100 volts to 240 volts. So this product is able to handle any voltage you provide between 100 and 240 volts, and it's able to power on. Now, there's also VA max listed. The reason the 20 VA is listed is to source out the proper supply line to make sure that this unit powers up. Now, 20 VA is not a lot of power, and you can see the calculation on the right here that this only draws 0.2 amps of current. So this is almost at the level of a cell phone charger when it comes to the power draw. One thing will tell you is that in a household setting, the limitation of power comes from the power breaker. The breaker is a 15 amps breaker, and some of the national fire code would not allow you to run more than 80% of the capacity, so 80% of 15 amps. So the max current you could get out of a household setting could be around 12 amps. Let's take a look at an example input label for a power supply. So this is a input label that comes from one of our power supplies. This power supply is able to take in different kind of power. You could power it up with a single phase 2-wire, again, line neutral. You could power it up with a single phase 3-wire, line 1, line 2, and a neutral. This also takes configuration of a 3-phase 3-wire. So if you had a delta power coming into your building or your lab space or any kind of power drop, this product will also power up with a 3-phase 3-wire configuration. And then your typical 3-phase 4-wire, which is the Y connection, you're able to power up with a phase A, phase B, phase C, and a neutral connected. So these are kind of examples of how voltages could vary for your input requirements. You have to specifically pay attention to what configuration they're asking for, and some products may have multiple configuration of input power available to them. All right, so now since we learned about power and power configuration, let's take a look at why we need to have power sources. So if the requirements you have that needs clean or regulated power, you may or may not get this from the wall outlet. So wall outlet depends on a lot of other equipments connected to the same outlet. You might see voltage that dips a little bit or sags or surges a little bit during sometimes when the motors come on. If you were to hook up your product that's sensitive to this wall outlet, it may or may not function properly. In order to provide clean, regulated power, you may require a power source which is able to do what we call line and load regulation. So on the input side, if the voltage fluctuates, on the output side is able to keep the voltage steady. Now this is what we mean by line and load regulation. Some of the power supplies offer really low total harmonic distortion. So when you're looking for, when you have a sensitive circuits, or when you're trying to measure sensitive equipment, you want to be able to make sure that there's no interference from any other products on your line. So having a low THD is really important when you're using power supplies. Now, power supplies, majority of the current generation power supplies are able to display the power factor of the load. Now, why is this important? Power factor of the load allows you to record how much voltage, how much power is being used and how much power is being delivered to the product, also how efficient this is. So a power factor of 1 will indicate a really efficient product. A power factor of 0.7 may indicate that the 30% of the energy is wasted. So if I'm a design engineer and I expect my products to be anywhere from 0.7 to 0.9, and if I'm running some tests on my products and I start saying 0.5 as my power factor, I should be concerned because my design specification doesn't allow power factor to be below 0.7. Crest factor is also something that's measured. Now, crest factor is what we call the peak of the RMS, peak value of a sine wave divided by the RMS. So if you have a really peaky sine wave, the crest factor is going to be really high. So you want to be able to make sure that you can measure the crest factor and some of the source that could even provide the power at those crest factors. What makes a power supply unique is that the power supply may be able to power up by variable frequency. So you could power up a power source at 50 hertz, but on the output, you're able to provide 60 hertz. So this is one of the benefits that's available. I've been to factory floors where they have a dedicated power supply for 50 hertz, and it's a huge space. It occupies a huge space around the factory just to have a dedicated 50 hertz power. Now, when we walk in, we're able to tell them that a power supply, a power source that could transfer frequency or convert frequency is able to take 50 hertz, 60 hertz in the input and deliver 50 hertz on the output. Now, this is where the output frequency and voltage ranges come in. So when you're looking at power supplies, you want to be able to make sure that it could output a different frequency than what was available at the input. Now, some of the requirements that come in for airplane applications or any kind of avionics applications, the frequency requirement may be 400 hertz because the power requirements for those applications, it may be 400 hertz, 800 hertz. So these are typical benefits you get taking in 60 hertz input and providing 400 hertz, 800 hertz, up to 1,000 hertz of output from the same supply. Now, we also run into a situation where a customer may have a product that's being tested for overseas. So they need to apply 230 volts and nothing around them has 230 volts. So in this case, you're able to take a power supply and deliver the proper voltages you need for proper testing. You could also convert single phase or split phase power and output into 3-phase power. So if you had a requirement for testing a 3-phase product, you either have to call an electrician to do a voltage drop for you for 3-phase, or you could buy power supplies that could output in 3-phase while only taking in a single-phase power. And there's additional requirements to do what we call line simulation. So if you want to be able to test line surges, brownout condition, also dropout conditions. So you want to be able to simulate how the DUT reacts to a particular line simulation of voltage going to 0, or it could be frequency changing on you in the middle of the cycle. It could be also just a little bit of surge, 110% of the voltage. It could be a dip of 90% of the voltage. How does a DUT react? Does a DUT stops functioning? Does a DUT cause any additional damage to itself? These are the conditions that people are testing to when they're using power supplies. Again, some applications of AC power sources able to generate worldwide voltages. If you have voltage requirements for 90 volts, you need to be able to have either a power source that could output this kind of voltage, and also some of the frequency requirements for the products being tested. Now, in order to provide clean power to your product, an AC source allows you to have a clean low THD, which is the total harmonic distortion. It allows you to have a clean power compared to a wall outlet. Now, a lot of the labs also have what we call test chambers that need to have energy star testing. And in an energy star testing, you're required to have a particular amount of voltage applied and for a significant amount of time. So not having any disturbances on this voltage application is a really important thing. So you want to be able to make sure that any source that you are sourcing out has this capability of doing a clean and a regulated power. So we talked about benefits of using a power supply. Let's take a look at the topology. So topology, we have traditional sources were designed with what we call linear power supply. Now these linear power supplies have a really big transformer in there. The transformer takes the input voltage, transforms it into a different voltage or frequency, and this is done by using operational amplifiers and some circuitry to make sure that the transformer is transforming the proper voltages. Now these are bulky. These are bulky in the sense that the transformer itself takes a lot of the weight. And it's really not that efficient because a lot of the energy loss goes into just powering up the transformer. The newer technology is known as a switch mode power supply. For switch mode power supplies, you have integrated circuits working in conjunction with other circuitry to provide what we call a switch mode power supply. Now, the main purpose of having a switch mode power supply is that it generates less heat, is much lighter, and is able to do all this by on a smaller footprint. Here's some of the comparison between a linear power supply and a switch mode power supply. So what do you get with a linear power supply? You get a really clean signal, low THD. It also suffers from efficiency. So the linear power supplies are not that efficient. They do have high operating temperature, operating noise, and they're heavy. Like I mentioned earlier, the linear power supplies are heavier than your typical switch mode power supply. Now, there's also fast response time. So when you have a linear power supply, the transformer itself is doing a lot of the work, so the response times is much faster. This is used for, it's best to be used for reactive loads, resistive loads. So if you have some kind of water heater or water heating element that's purely resistive, a linear power supply may be able to power it up more efficiently. For a switch mode power supply, since we're making this signal, we're converting a lot of the DC into AC signal, you may experience additional high harmonic distortions. So a switch mode power supply does suffer from a high THD, but it's more efficient. It's more efficient in able to convert energy received from the input to energy being outputted at the outputs. Now it also has low temperature and low fan noise, and it's also lighter because it doesn't have the transformer that's required for a linear power supply. It's best used for reactive loads. So if you're trying to power up a reactive load that may have a higher crest factor or a higher inrush current, a switch mode power supply is able to handle these additional requirements because you're actually adjusting on the fly of what the output may be. So majority of times when you have a motor that needs to come on or an inductive load that has a requirement for high inrush current, a switch mode power supply is able to handle this properly. It does have a slow response time. Again, since we're doing a lot of signal modification, we're taking the signal, we're doing the pulse width modulation to this, make it into a square wave, and the square wave is then filtered out at the output. There is some response time, response time for converting the energy from input to the output because it goes to these phases. Again, some additional benefits of having a switch mode power supplies. Majority of the power supplies that APT manufactures are switch mode power supplies, and the benefits, again, I mentioned higher efficiency, significant weight reduction, ideal for reactive loads. A lot of the products we see out in the market or in the industrial setting is reactive loads, being able to power up these reactive loads. All right, so since we learned about having these different types of power supplies, what would you need to check for when you're sourcing out a power supply? Now, the first thing that I would look for is the power output. Now, if I have a product that needs to power up, I want to be able to, I need to be sure that this power supply is able to sufficiently meet the power requirement. So take a look on the right here. We have an example of power rating from an oven. The oven requirements at 120 volts, maybe 120 volts to 240 volts, could be anywhere from 8.8 kilowatts to 16.5 kilowatts. Now, I need to be able to make sure that my source is able to output at least 16.5 kilowatts of energy. Now, electric ovens or electric range are much higher requirements on the current, but if you had a simple example of a vacuum may need maybe 500, 600 VAs. At that point, you still need to make sure the power requirement of the source meets the power requirements of the product is met by the output of the power source. You will also see the voltages. Now, the voltage differential between input on labels that we saw earlier, it may require you have a voltage from 200 or 100 to 200. So you want to be able to ensure that you're able to test at a particular voltage that's required by your standards or required by your product. Some of the ranges that you may see is 0 to 300 volts in single phase 2-wire. Again, this is line neutral. Some of the output voltage for single phase 3 wires is twice the output in single phase 2 wire, which will be 0 to 600 volts. Now, when it comes to 3-phase configuration, some of the source might list out voltages anywhere from 0 to 520 volts. Now, these are voltages listed for 3-phase, phase-to-phase voltage, also known as the line voltage. So we looked at power requirements for your product, the voltage requirements for your product. The additional items that you want to check is the current draw. So when we look at the input labels for the products, you're going to see what is known as a steady state current. Now, a max current that's listed on the product, you want to make sure that the product specification for the source specifies that it meets that current requirement. You may also want to consider inrush current. So there's times when inrush current could be up to 10 times more than the steady state current. And as you will see later on in the demo, when we're trying to power up this vacuum, full household vacuum, the inrush current requirements are much greater than the steady state current requirement. And we're also going to take a look into how you could source out your products to meet these requirements. Crest factor. So when we have non-ideal loads, non-ideal loads would skew the sine wave in such a way where the peaks are much higher versus the RMS value. So when you have much higher crest factor, you want to be able to make sure that the power source is capable of driving these loads. A motor, an inductor, some kind of a combination of heating element with some other motor in there, it may require you to have a non-ideal sine wave. Is a power supply able to handle these crest factors? A sine wave, a pure sine wave, has a crest factor of 1.1414. Now, this crest factor could go as high as 3 or more for some of these loads that are connected to a power supply. So you want to make sure that the crest factor is addressed in your product specification. THD, total harmonic distortion. So again, we mentioned that switch mode power supplies suffer from high THD. If you're looking for a clean power, or you want to make sure that THD is as low as possible, prefer less than 1%. Since we're producing a sine wave from these circuits, we want to make sure there's no other components of the 60 hertz sine wave added to the main component at 60 hertz. And the last thing you want to check is the input configuration. So there's a lot of confusion of how the power source needs to be powered up. Recently, we dealt with a customer where they were confused about how the power source is going to power up, plus deliver this additional output. So you want to make sure that input specifications are noted down, and there's enough available power to power up these power supplies. Since we've been talking about the specifications, let's take a look at one of the input and output specifications for a 300 XIC series power supply. For this power supply that APT manufactures, the input specifications are listed here, and really quick going to show you the phase voltage. You could have a single phase that powers up 3 of these power supplies, and additional a 360, which outputs up to 6,000 VA, requires maybe a 3-phase power supply. So you could power up a 360 XIC with either single phase power or a 3-phase power, and the voltages required for each phase or each configurations are listed here. For a single phase, 200 volts to 240 volts could be required. In the 3-phase configuration, you may have anywhere from 200 volts to 240 volts. Now, frequency on the input side, you could have a frequency anywhere from 47 to 63 hertz. So again, when you have input frequency that varies between 50, 60 hertz, or a little bit higher or lower than 60 hertz, the source is able to handle different variation in the frequency, but still deliver output at a steady level. So the input would not affect your output drastically when the frequency varies by a few percentages. Taking a look at the output of this series, the output in a single phase, you could get anywhere from 5 volts to 300 volts. Each instrument has its max power rating, a 1 kVA power supply, 2 kVA power supply, and so on. The way we get this power rating is that we multiply what is the max current it could do and the voltage it could do that current at. So this power supply could deliver 9.2 amps at 110 volts. That makes it a 1 kVA power supply. So if you had your requirements, your product specification label that says 800 VA, this power supply may be able to meet your requirements for 800 VA. As long as the current maximum is not more than 9.2 amps at 110 volts, or the second range, which is a higher range, is going to be 4.6 amps at 220 volts. So the reason the current is half is that it allows you to do much more voltage, and we're conserving energy here. So when we do, if the current decreases, you're allowed to increase the voltage and not affect the power rating. So 4.6 multiplied by 220 still gives you the power rating of 1 kVA. Now, this might give you a little bit more over 1 kVA, but the specification guarantees you that the instrument or the supply will deliver at least 1 kVA of power supply. 1 kVA of power. Additional configuration may be possible. So if you were to combine 1 or 2 of these products, or maybe 3 products, 2 of these will give you 2 HOTS. Again, 2 HOTS is single phase 3-wire connection. If you link them again with the configuration of having 3 of these products, same products lined up on top of each other, it may be able to generate 3-phase power. You're taking in single phase input from your wall outlet, and you're generating 3-phase at the output. Frequency output, this is another important thing. We're able to generate anywhere from 40 hertz to 1,000 hertz. So your application that requires 800 hertz, you don't have to go out and look for some frequency generator, because you have the source that's capable of driving this kind of voltage and current at these frequencies. We mentioned THD, less than 1% is ideal. This one's usually listed for resistive load. And we mentioned crest factor. So initial crest factor, we allow up to more than 3, and continuous crest factor, again, more than 3 at 110 volts. Now, these are listed to make sure that the power delivered to your product is able to handle any non-ideal load, which may skew the sine wave up or down. So again, if you were to, if you knew your voltage for your product, let's say 100 volts is requirement, or 120 volts, your US standard voltage, and I need to have a 4 amp power current draw. So 120 times 4 will give you 480 watts or VA. So 480 is what's required. 1 kVA for power supply is almost double the power, and this is enough to kind of drive the load that you need. So this brings us to our second poll question. So hope everybody was paying attention to what I just described. We're gonna kind of put up a question on, based on the power requirements of having 200 volts and 10 amps, what is the power supply you would choose? And your options are listed here as a 1 kVA power supply, 2 kVA, or sorry, 2000 VA, 3000 VA, 4000 VA, or 18,000 VA power supply. So I'll have Amanda put up the poll question now.
Hi, Bashan. The results are in. Okay, so based on power requirement, select the appropriate AC power source to power a load of 10 amps at 200 volts. 0% said 1,000, 60% said 2,000, 20% said 3,000, 20% said 4,000, and nobody said 18,000.
All right, thanks everyone for submitting the poll questions. So it's good to know that 60% of you selected 2,000 VA power supply. Now, this may be at the edge of the requirements, but if the power source is specifying that it could deliver 2 kVA or 2,000 VA, is enough to meet the requirements. Now, some may be cautious and buy a power supply maybe at 3,000 VA to ensure that you're not operating at 100% of the capacity of the power supply. So the correct answer could be 2,000 VA or 3,000 VA, depending on what the requirements are. Do you want to operate it at 100% of the output capacity, or maybe at 80% or less? So let's see how we could do this. Power is, again, voltage times the current, V times I. We already knew what the voltage requirements was, and then the amps that it could draw is 10 amps. This gives you a power of 2,000 VA. Okay. Moving on. So again, this is just more of what we covered earlier. If I had a 3 horsepower single phase motor, if I was looking at the specifications that it requires 230 volts at 60 hertz, 13 amps needs to be drawn. 13 amps could be drawn at 230 volts. Multiplying these two numbers gives me a power requirement. Gives me a power requirement of 3,036 VA. Again, this is a little bit over my 3 kV power supply if you had one, and then having a 4 kVA power supply would be efficient or sufficient enough to drive this load. Some of the capabilities of the source is 0 to 300 volts is met by 0 to 300. Frequency range is 60 hertz. Source could do 40 to 1,000 hertz. The current requirement is at 13.4 amps at 230 volts, while the source could output up to 18 amps at 220. So you're still not exceeding the max current limit, which is important to note. There's times when you may have max current listed and the source is not able to drive that max current at that particular voltage. Again, this is a 4 kVA power supply, able to deliver sufficiently deliver 3 kV power requirement. Additional features or technology. So now since we know what power supplies could do, it could convert input frequency, input voltage to a different input output frequency, output voltage. What are some of the features that you look for? Does your product or does your power supply have a technology to kind of allow you to have a much higher inrush current? So when the motors first start spinning, it has a requirement to much more power draw, or much more current is being drawn. But once the motor is already spinning, it may not require the same amount of current. So this is what we call an inverse period requirement for having a lot more current for the product, and then a steady state steady state area where the motor is already spinning and it doesn't require that much current to keep it spinning. With a technology like OC fallback, it allows you to power up loads that may be beyond the requirements. So let's assume that if you had a much higher requirements for the current draw, it just pushed you right over a 2 kVA power supply. But for the inrush time, the motor requires almost 3 kVA of power. Well, how do we address this? The way we address it is that we let the motor power up at the 2 kVA power supply using an OC fallback technology where the voltage is lowered to allow the high inrush of current. So the voltage may sag for the few milliseconds or a few seconds that the inrush period is there, but when the inrush period is over and when it returns back to a steady state state, you now could increase the voltage back to the proper voltage. So this allows you to power up really inductive or capacitive load that have high inrush of current. We do have a demo of OC fallback after this slide, so this is where I'll demo how OC fallback feature works. Another demo we have is for the transient functionality. Now again, you want to mimic power line condition. What are power line conditions? So we may in the US get stable power, but there's locations around the world that the power is not stable. Do you want your product to be out there and not work properly? But if you don't, you need to run some tests to it. So you want to be able to run some surge testing, some dropout testing, some brownout condition testing. These are all some of these technologies that newer power sources allow you to do. PC control, some of the automation-wise, you want to be able to control this power source by the PC. So it may be an important feature to have a full control of your power supply using a PC or some kind of relays, A DC output is also a feature. Some of these sources now allow you to have both AC and DC outputs from the same power supply, and it'll also have different specifications listed out for the DC power supply. So let's take a look at a demo from OC fallback. I'm going to describe you the functionality. So what we have here is a front screen of our 300 XAC series. This is a 2 kVA power supply. So obviously it allows you to run a test and provide up to 2 kVA of power. We have set the output to 240 volts. The max current available at this voltage will be 9.2 amps. So what we're going to do is we're going to apply voltage to this motor. This motor has a really high inrush current, so it's going to require 13 or 14 or 15 amps of current. Since the power supply is not capable of delivering that power, it's going to shut off. It's going to shut off and say a high limit failure. So let's take a look at what happens when we do power up this motor using this power supply. And you can see here where we're outputting 240 volts, and I'm going to pause this for really quick and take a look at the failure message, A high. It exceeded the current available for this power supply. It tried to draw up to 12.71 amps at the last meter reading. A peaks or the power amps were peaking out at 13.5 amps. So again, this source is not capable of powering up this vacuum. But the feature that allows it to power up is called the OC fallback. And what we are going to do here is going to quickly turn on the OC fallback feature. And when we turn on the OC fallback feature, you will see that the voltage is going to sag. And when the voltage is sagging down, the current requirements are met, and the motor starts spinning, and the voltage will come back to appropriate level once it goes into a steady state. So quickly here, we're going to just make sure that our OC fallback is turned on. That's the only thing we turn on is a feature called OC fallback over current fallback mode. And in doing so, this allows us to run this vacuum motor successfully past the inrush stage. You can see here that we're applying 240 volts. And then when the motor turns on, it draws 19 amps. So I saw 19 amps come up there for a few seconds. The voltage was dipping. And then what we saw additionally is that now it's to a steady state. So this power supply could meet the requirements for steady state, but was not able to meet the inrush requirement. But having OC fallback allowed it to power up this vacuum motor successfully. A few other meters that we could take a look at really quickly is frequency is what we are measuring for this output. The amps are shown here is the same value as the amps that are being measured. The power, now we talked about power in watts. This is the actual power that the motor is using to do some work. So if the vacuum motor is doing the work that vacuums, but this is the amount of energy that's being used. If you take a look at the right here, you're going to see VA. So this is the actual power that's being delivered. So previously we learned that power factor is the efficiency of how much power is being delivered to the product and how much work is being done. And the way you know that is that the power factor is being calculated by dividing VA or the total power divided by the real power. And then you also see crest factor. So when I mentioned earlier, a crest factor of a sine wave is 1.414. This product is a non-ideal product, a motor. So the motor skews out the sine wave, and the crest factor of this sine wave is 1.79. So it's more peaky, and versus being a ideal sine wave. The next demo we have here, a demo of transient. So what transients are, like I mentioned earlier, that you are allowed to, if your requirements ask you to drop the voltage down for 10 seconds. How would you achieve that? So on this motor, I have 240 volts being applied, 60 hertz is my frequency. Now I want to be able to drop the voltage down to 120 volts, so half the voltage. How does my product react when I drop the voltage for 10 seconds? Transient time, which is the next parameter, is telling you where on the sine wave you want to drop this. Your product might react differently if you drop the voltage when it's at the peak or just at the starting period. So this is where on the sine wave you want to drop the voltage, and the trans time is how long you want to drop it for. So our maximum parameter for this product is 999 milliseconds, so 1 second. And since I want to drop the voltage for 10 seconds, I'm going to make this a 10 cycle programmable transient. What you're going to see on the next screen here is that we're going to output. So the voltage is currently being outputted. There's an option to trigger this transient. So a trigger is a soft key here. Either it could be programmed. On this one is a manual. And when I press trigger, you will see that the voltage is being dropped to 120, and it's going to drop this for 10 cycles, which is 10 seconds, and the voltage is going to come back right up at 240. So what we did there was we allowed the voltage to operate at 240 and then drop the voltage down to 120 for 10 seconds. So these are line simulation when you're trying to do some transients. So towards the end of this webinar now, so this is how power supplies are used in some other applications. Electrical safety testing is one of the important aspects of doing product testing. When you're testing some medical devices, some of the standards like 60601-1 require you to have 110% of the power. Now, the 110% of power may not be readily available. So if you had a product that's listed at 230 volts, you have to be able to provide, or 240 volts, you have to be able to provide 264 volts. So in the setup here, you see that a source is being used to apply power for a device to turn on, not at the normal temperature, but not at the normal voltages, but at the voltages at 110% of the rated input voltage. Take a look at some of the other requirements for other standards. UL 508 requires you again to have 110% of the rated voltage applied to the coils and make sure they're operating without damage. Audio, video, electrical apparatus, they may require you to have a dip of 90% of the voltage. So how do you achieve all these voltages from a wall outlet? So you need to have a source that's capable of driving the load and driving the load at proper voltages. And then lastly, we have this LED requirement, LED equipment that also requires for you to raise or lower the voltage within the 5% of the mark voltage. So a power supply allows you to manually raise the voltage or program it to kind of go from 90 volts, 100 volts, 115 volts, but it allows you all these controls on the fly. So you're able to change the frequency on the fly, you're able to change the voltage on the fly, and these are some of the benefits and applications of power supplies. This actually concludes our webinar for today. Additional resources are available on our website at aptsources.com. I'm an application engineer. I'm also available to answer any questions. So is my colleague Syed. And if you have any questions, you could either use the chat box right now, and I'll open up for questions and see if you guys have any questions that I could address.
Yeah, Bishan, I don't see anything much on the chat line, so no questions there.
Okay. All right.
Yeah.
Yeah, and again, if you have any questions, do email us or reach out to us using our website. And if you have any questions about the presentation, or if you need a copy of the presentation, do reach out to Amanda Booth. The webinar is recorded and it will be available online. Our next webinar is back to associated research, electrical safety testing, so leakage current testing 101, October 10th at 10 a.m. Central Standard Time. And some additional resources for consulting. We do offer application consulting more on the electrical safety side, but also on power side. If you require us to kind of come in and kind of figure out what the capacity of your power supplies you have currently and how we could efficiently provide solutions to you. Again, contact us if you have any questions, amanda.booth@iconixusa.com. Thanks everyone for attending.